Hi there. Welcome to Big Ideas at µScale. My name is Hemdi Patel. I am co-founder of Creative CADworks 3D, and ResinWorks 3D. My co-host, Robin. Robin, how are you?
Good, I'm good. Like you said, I'm Robin. I'm also a co-host, and I'm the technical writer on the marketing team at CADworks 3D.
And so today we've got a team from a institution that's very close by. In fact, I used to work downtown for the better part of close to 20 years, and I used to always walk by up and down the street that would be adjacent to this place. It was St. Michael's Hospital. It had new name changes, and I had the opportunity to, while I was there, had an opportunity to first talk to Dario, who leads the microfluidic manufacturing division at what used to be St. Michael's, and I think it's now Unity Health. And I'm sure Dario is going to sit down and explain all the intricacies and all the changes that has been happening there. And along with him, we'll be joined by Stephanie and Niloofar, and they are part of the team from Dr. Scott Tye's lab. And they've got some very interesting research that they're doing on I think I'll have them describe it. So why don't I bring them on board? Dario, Niloofar, Stephanie, welcome.
Thank you so much for having us.
Hello.
Thank you.
Thank you.
Yeah. So Dario, why don't you sort of give us your CV and what you do at this lab, and I guess everything pertaining to microfluidics.
I work as microfabrication specialist at the Research Core Facilities Department at St. Michael's Hospital Research Institute. Yes, we are part of Unity Health Toronto, but still St. Michael's Hospital. Also, we have a partnership with Toronto Metropolitan University and iBest Institute. So we offer facilities, expertise, and training to our users here at Research Core Facilities. So the core that I'm representing is called Microfabrication core, so specialized in microfluidics device design, development, and small-scale manufacturing. Also, we have analytical equipment. We also offer some 3D printing capacities, laser cutter.
Well,
that's what we have here.
So I think the first time that we spoke was in 2019 or so, and I think at that time you had come to our office down when we were downtown, and there was, I think, what was it at that time that you were looking at? Was there a need that you guys were seeing at that time, or was it just a curiosity of how 3D printing could work for you guys?
It was both. It was both. That was early stage of the core that I'm representing here. We were in kind of construction phase. We were looking for new equipment. And at that point, 3D printing for microfluidics was at a very, very early stage, but it sounded like something that is coming as big and promising in the field. I found your company here, and it was basically neighborhood, and that's how it started.
Yeah.
There was not that many companies like in the field in that time.
Yeah, that is true. Niloofar, how about you?
So I'm, as you said, Niloofar. I'm finishing up my PhD in biomedical engineering. Just finished my fourth year, and in 3 weeks or less is going to be my PhD defense. I haven't studied yet, but from next week I'm gonna study on the material and everything. But so far, no worries. So my project, my supervisor is Dr. Scott Tye, as you said, and our lab is at iBest. which I think we are really grateful. And I always say that we shouldn't take for granted that our lab is at IBES, because IBES kind of have everything that, and also like some really amazing people. And because there are lots of like different labs that they're working on different things, it's really amazing in a way that you can collaborate with different people and have a really good project, because everyone is like from different expertise. And so for the first time with Dr. Ghasenzaie, I started working on microfluidics, and Dario was the one that first taught me how to use Cleanroom, how to make microfluidic device using soft lithography. And again, Dario was the one that introduced 3D printing in our project.
Amazing. So how about you, Stephanie? What is your experience, and how do you fit into, I guess, IBES and the lab there?
Yeah, for sure. So like you said, my name is Stephanie. I'm a recent graduate from like the Biomedical Engineering undergraduate program at Toronto Metropolitan University. I graduated just this past April. And I just recently began my master's degree as well in under the supervision of Dr. Ghasenzaie. I'm also co-supervised by Dr. Michael Kolios at TMU as well. And I'm the same. So Dario was the first person that introduced me to like clean room operations, so photolithography, soft lithography, and recently he's trained me on how to use 3D printing for microfluidic applications as well. So in Dr. Ghasenzaie's lab, we do a lot of microfluidics work. So my project also focuses on using microfluidics.
Amazing.
So is it that IBES is kind of like the connecting point between TMU and St. Mike's Hospital? Is that how it works?
Yes, yeah, that's partnership between St. Michael's Hospital and TMU.
Okay, so you're training a lot of students in that case, Dario.
We have quite a few groups here that are interested in microfluidics and microfabrication.
And so then Stephanie and Niloofar, you were saying that the first time that you were introduced into 3D printing, that was through Dario, right?
Yes.
Yes, exactly. And also he was the one that talked about getting a grant for 3D printing, and asked for my help to make some fibers using the 3D printed device, that sample that he had, to write the grant. And he was successful in getting the grant and bought this amazing 3D printer that helped lots of people right now, the students at IBES.
Were you using a different technology before 3D printing? So for example, Niloofar, you're doing fiber fabrication. Stephanie, you're doing, is it microbubbles or nanobubbles, or is it both?
Yes, so we microfluidically generate microbubbles, but these microbubbles, they shrink down to nanoBubbles. So the final product is a batch of monodispersed nanobubbles.
So both.
A little bit of both, yeah.
Makes sense. I mean, they're hand in hand, really. So
yes.
So when you first started the research, did you kind of already immediately know that about 3D printing and that maybe this is the direction that you were going to take it? Or was that you just came to Dario, for example, and said, this is what I'm working on. What are my options?
For my case, it was my supervisor was actually the one that suggested that we try using 3D printing, because the traditional mechanism of making our microfluidic devices uses the photolithography, soft lithography. The process is a little bit tedious. So we thought it might optimize the procedure a little bit more if we could actually translate it into a 3D printed platform.
Yeah, so for me, it was Dario that suggested that, and also the way that, so for me, I guess the case was different, and the way that I spent the first 2 years of my PhD making that microfluidic device, and most of the time I wasn't doing the experiment, I was making the device. For days, I was just filing some glass capillaries and stuff. So it helped me so much. For me, it was just make the device fabrication easier.
Yeah, the idea comes from the project that Niloofar is doing, and there was very labor-intensive process of making these devices. So we thought, how about we incorporate 3D printer in general, even before knowing about those ultra high resolution 3D printers used for microfluidics, and maybe combine it with capillaries to assemble device. And that's how it started. And then we ended up actually using the Profluidics printer, that we can print the entire device without combining it with capillary, which of course is one step further. And now we can do entire device, including even the connectors and everything that we need to use it to extrude the fibers. So simply just connecting it to the external pumps and tubing and start experiments. I think that helped and in Niloofar, and also reduced time for making device significantly. Also enable people to without previous experience with photolithography to start making microfluidics devices, which is also very important aspect of having the 3D printer, such as Profluidics.
So now, in terms of I do want to touch on all of the research that you guys have been doing, but if we were to take one step backwards before knowing this is an existing 3D platform, what was the original steps like? What was involved in order to make these capillaries and any of the devices that you were working with?
I can speak to my experience first. So for my devices, I didn't really need to integrate any capillaries or anything like that. It's a little bit more of a simplistic process, I would say, than Niloofar's devices. But making the microfluidic device, so first incorporated like photolithography to actually fabricate like a silicon wafer where the microfluidic channels were kind of patterned onto it. So this was like a clean room procedure. It takes a lot of time. So there would be a CAD design that would be fabricated onto the wafer. And then following that, so I would be able to use that one wafer like time and time again to make my actual like PDMS based devices. And the PDMS based devices were made using like soft lithography. So a liquid PDMS would just be poured over top of the wafer, cured, and then peeled off. And I was left with the channels transferred onto a PDMS block.
And then, so now, if you were to look at in terms of time, what was the how much time did you put into a few days, a couple of weeks? How was that?
Yeah, so in terms of actually the fabricating the wafer itself, that's something that usually takes like about a day in the clean room to fully complete. So from just fabricating the wafer. And soft lithography is something I do need to repeat every single time I run an experiment. So I can't really reuse one single device. I have to continuously make new ones. And we also have to bond them to like a glass slide so that the channels are enclosed. I have to make my channels hydrophilic as well for my purposes. So I require like additional treatment that way. So that's something that needs to be repeated like every single time I run the experiments. And so about an hour before the experiment.
Wow.
You said like it's a little bit more of like a simplistic design, but did you find that you needed to have a lot of different like small design changes and like changing the silicone wafer and everything like that? And did that kind of like delay a lot of things for you?
Yeah, partially. Like the design I used was something that actually is kind of standardized for my protocol. So previous students in my lab. So for that reason, I'm kind of grateful that I didn't have to go through a lot of iterative design like that. So yeah, for me, it was a little bit easier I didn't have to do a lot of CAD iterations, but I know with photolithography, it can be pretty tedious when you do have to do a lot of iterations of a single device. Obviously, you'd have to repeat that photolithography over and over until you get it right. So that can be a very time consuming.
For you, it was fine. That's great. Oh, could you actually explain a little bit about your device design, its applications, that sort of thing?
Of course, yeah. So my device design, so it's essentially a flow focusing geometry. So I have two inlet channels in my device. One is going to be like a dispersed phase that is a gaseous phase. And then I have also like a continuous phase of my device, which is going to contain like a lipid solution. So the bubbles that are generated from they kind of pinch off of the flow focusing orifice, and they're microbubbles, and they're shelled by this lipid solution. And we use a gas composition of like a low solubility and a high solubility gas mixed together. And that it like influences or facilitates dissolution of the like high solubility gas, and it allows my microbubbles to shrink to very small nanobubbles. And because we're using microfluidics, it actually allows the final size distribution to be very monodisperse and size uniform, which is ideal for applications. So the reason we make these bubbles are actually to be used as in contrast enhanced ultrasound. So they can be injected into the bloodstream to actually enhance the contrast of the blood pool in the body. Nanobubbles are not quite clinically implemented yet, but microbubbles, those are already clinically implemented. So the reason why we're interested in like monodispersed nanobubbles is because in the body, they demonstrate potential to enter extravascular space and expand applications into like a different area beyond the bloodstream. So that's kind of the purpose of my research as well and the work that I do.
And so, by a factor of how much does these bubbles shrink by from the micro to the nano size?
So we actually find that there's kind of like a critical diameter that they need to be initially to facilitate complete nanobubble dissolution. When it's above this critical diameter, so it depends on a lot of factors. It also depends on like the concentration of the solution we're using and things like that. When they are bigger bubbles, they will kind of shrink by like a known factor, like so by 10 times or something like that, we can predict it. When it's below that, it's kind of a critical diameter, we call it, they will always shrink down to like 200 nanometer size, like in diameter nanobubbles. So that allows us to facilitate like really great monodispersity since we see a really, really tight size distribution centered at like 200 nanometers, which is great for controlling like the response of these bubbles under ultrasound as well.
Wow.
Does the channel of the size, the flow focusing channel size, does that affect kind of like how much it shrinks by, anything like that?
Not so much the actual channel itself, but the flow focusing orifice, that plays a big role because ultimately like the size that we can make the microbubbles at is kind of dictated by the width of that flow focusing orifice.
And so on using, I guess, 3D printing, how small are you able to get some of these droplets, I guess, in this, or these bubbles?
Mm-hmm. So this is one area where I've definitely had, I guess, the most struggle at the moment. Obviously, so with fabricating actual like channel geometry on the order of like a couple hundreds of microns, that's been pretty easy to do using like 3D printing. However, the flow focusing geometry itself, like typically we like to see that on like the order of like tens of microns, which is a little bit difficult to fabricate currently, I guess, with current resolution abilities. So kind of a couple ways we've been kind of thinking to get around this is maybe like integrating a microporous membrane or something like that instead of a flow focusing orifice. So it does kind of incorporate another fabrication step, 3D printing, and then also the embedding of a membrane. We haven't done this yet. This is just kind of ideas that we've been shooting at about how to overcome the resolution restraints. But yeah, that's kind of some thoughts that have been going into how we can actually generate these bubbles and still have them be small microbubbles with resolution.
How about imaging or even just analyzing the bubbles? Do you use like microscope imaging or is it like a different measurement system?
You mean during like the actual generation procedure?
Yeah, so once you generated bubbles, I don't know if you've gotten this far, where you've already generated the bubbles and now you need to study them, whether it's the uniformity or whatever it is.
Yes.
How does that work for you?
So in terms of like while they're being generated, so typically when we have like clear microfluidic resin or even with like PDMS in the past, it's optically transparent. So we can actually like visualize what's happening as the bubbles are pinching from the orifice. But and when they're microbubbles, we can actually see them under a microscope. When they shrink to nanobubbles, it's a little bit difficult to visualize with like a traditional light microscope or something like that. So there's a couple ways. So we can actually visualize like the bubbles using like TEM imaging. That's one way we can do it, but it doesn't really allow us to gather like population characteristics well. So the way we mostly rely on is actually called resonant mass measurement. So it uses like a cantilever that's in like has a microfluidic channel that's embedded inside of it, and it resonates. So as the bubbles pass through, depending on their mass, it will kind of change its resonant frequency slightly, and we can derive characteristics of the nanobubbles that way. Dario might be able to speak more to this as well, because this is a device we actually have in iBest as well.
Yeah, that's an interesting analytical instrument that we have and pretty unique. It's based on microfluidics sensor that can detect particles based on their buoyancy. And that's what is preferred when analyzing the nanobubbles, because you want to clearly distinguish between the bubbles and the residual lipids. And since this instrument can recognize the difference buoyancy, positive or negative, so you can clearly see what particles are bubbles, because they are positively buoyant, vs the other particles, negative buoyant particles, or those that would sink or float.
So it allows us to get around the restraint of the fact that they're so small and we can't really see them under the microscope.
Wow. So now, for Dario, when in your lab right now, you're obviously bringing in a lot of tools together in order to help researchers. What additional tools do you have at the lab that a typical researcher team will use?
So we have 10,000 class clean room, so that's ISO 7. That is specialized for photolithography. So we have a standard classic mask aligner, then we have a maskless aligner tool, optical profiler, and of course wet bench with spin coaters and hot plates. So we have everything that is needed for that traditional standard photolithography. Also, we have a suite of analytical equipment. We just mentioned the Archimedes. We are focusing on the particle analysis because most of our users are either in the area of nanotechnologies or making, including nanobubbles, but also lipid nanoparticles or some other type of nanoparticles. So we are providing instruments such as DLS. Most recently, we got NTA. We have advanced spectrofluorometer, spectrophotometer, Coulter counters, and that would be for analytical side of the core. We also offer the 3D printers. We have standard Mark II printer extrusion type. We have Profluidics that we got more recently for Microfluidics printing. We also have one laser cutter. Just to mention that that microfabrication core is actually part of research core facilities, and we have another 5 cores that are specialized for flow cytometry, imaging, histology, and we are all situated in the same building. So basically we have 4 floors, and each floor has 1 or 2 cores specialized in some area.
And that's all at that the Likashen building.
That's
correct?
in Likashen building, downtown Toronto. We are very close to Eaton Center.
Dario, in terms of the work you guys are doing, you're obviously helping a lot of researchers through that building itself. When they look at 3D printing do they look at it as an alternative to Cleanroom, or do they build their project based on that they are going to 3D print this?
Yeah, we have users that actually use the 3D printer, Profluidics, as alternative to Cleanroom. So for few reasons. So first, it's doesn't require photolithography skills and knowledge. Then you can definitely reduce the cost of materials, and probably the most important is time, as Stephanie already mentioned. So you can get ready-to-use device in a matter of 2-3 hours. Plus, 3D printing is pretty much walk-away process. So, and that's probably the important things. But we also have users that are looking for, who are very experienced with photolithography and all this aspect. They're not really problem, including time. Yeah, time in clean room, depending on your device, could be everything from 1-2 hours, which is comparable with the 3D printer up to whole day, as Stephanie mentioned. But what people are looking are some aspect of the using 3D printer that you can't do using the photolithography. So you can do some geometries that are impossible or would be very difficult to do using a standard photolithography process. And that's, for example, case with the Niloofar device using the capillary, where we printed 3D shaped nozzles that helped to establish this core of fiber that is required during the flow focusing process to extrude the fiber out of the device. And that helped significantly in terms of getting device. Previously, we would need to insert the capillaries inside the PDMS device, which would be very tricky, and repeatability was not so great. Like here, we have device in a matter of 2-3 hours without any additional work on device fabrication required. Simply like plug and play device where you connect with tubing. And another also interesting and very appealing aspect of 3D printing microfluidics is that you can print connectors as a part of your device, so you can just connect either simple tubing or tubing with the fittings, like threaded fittings, with no problem. And we tested that with multiple devices, and that worked really well.
And then, so when most of the people are coming in, are they wanting to print clear or PDMS? I know that we've spoken a couple of times where you've had researchers actually building out their own photopolymer with specific characteristic. Is that sort of the type of
that's still an ongoing project, but primarily we use the CADWorks resins, including clear one, which is favorite one because people get ready to use device. But we do have users making the PDMS master molds out of, I call it green resin. And that also is one of the interesting aspects. And again, I'm saying because not only that save your time of making device when you compare to microfabrication using standard photolithography, but you can easily create multi-layer device, of course within the resolution limits, but I believe with green one we are down to X5 50 microns. That's something that we tested, and that doesn't take any more time than when you would do single layer. And everyone who is in photolithography knows that making multiple layer devices is usually thing that is time consuming and can take you whole day in the clean room, especially when you need to do alignment of multiple layers. While here, simply technically there's not much difference if you have one layer on your master mold or you're making something that we call multi-layer device. So, and that's, I think, also very interesting and useful aspect of using PDMS master mold. Of course, there are some limitations, and that's with resolution that you still can get using the photolithography. With photolithography, we can easily go when we use SU8, and that's called soft lithography techniques, down to maybe 5 microns, some features.
Stephanie, out of curiosity, which material are you using to build out your generators?
I was also using the clear microfluidic resin as well. Yeah, just for my purposes, it's really helpful for me to visualize the initial size of the microbubbles under like the microscope while they're being generated. So it's really helpful for me if I have a clear material so that I can make sure everything is up to par before I start collecting them actually and characterizing them later. But for my purposes as well, it might be beneficial to use like maybe like the green material or something like that, just because of the resolution improvements that we can get with that. So it's kind of for me like a balance between the two of those.
How important was it to have and maintain really good laminar flow in your devices, Stephanie, in order to sort of standardize the size of bubbles that you were getting?
Yeah, it's pretty important just in terms of like the stream of bubbles that's being produced needs to be very like smooth and consistent. Like it's the size that's coming out of the orifice needs to be very consistent. That's also why it's important for me to like monitor what's going on in case there is like an obstruction or something. Even the hydrophilicity as well of the channels is something that really influences how smooth that stream and monosperse the stream of bubbles is coming out. just because, as I mentioned, there is like a kind of a critical diameter. So every bubble below that is going to be able to shrink to a nanobubble. The bubbles above that will not be able to. So if my bubbles are kind of fluctuating in size when they're coming out of the orifice, it's going to be like I might not have a very high concentration of bubbles in the end, or I might have like a very a wider distribution, which is kind of not ideal for my work.
And how you said something quite interesting, the hydrophilicity. How did you sort of modify that on the clear itself?
Yeah, so traditionally with PDMS, I used to use just like I still do with the oxygen plasma is able to induce hydrophilicity. So I actually I haven't actually like created bubbles within the resin device yet, like with the hydrophilicity induced and everything. But I did put a block, like just like a device that was pre-made in my oxygen plasma cleaner that I have in my lab as well.
Yeah.
For I think it was just about 30 seconds, I turned on the plasma and I just put a droplet of water on the surface of the device. And I noticed like a big difference in the contact angle. So it did definitely induce hydrophilicity on the surface. Okay. And since the channels are open as well, I would kind of speculate that it would also have improved the hydrophilicity of the channels as well, since the inlets are open to the atmosphere as well. Yeah. Mm-hmm.
Was there any other surface modifications that you had to do besides the hydrophilicity?
For me, not really. I don't really do any like cell culturing or anything like that with my devices. So just hydrophilicity is the main thing for me.
Okay.
Yeah, we have another project where a user is interested in having hydrophobic. I mean, the clear resin is hydrophobic by itself, but this is something that is required for droplet generation, where it's required salinization and get it like hydrophobic in a sense that is that you can generate the droplets using the fluorocarbon oils. And that's something that we are also looking into and some ongoing project. But based on literature and discussion with CADWorks is something that is doable, and that channels can be silinized and something similar to PDMS, so make them acceptable for droplet generation using FC oils, which is very common application nowadays in droplet microfluidics.
So, Stephanie, you did all your undergrad at TMU?
Yes, I did. I began undergrad in 2021, so back during COVID, and finally things opened up around my second year, and then I just finished in 2025.
Wow. There was a, I don't know if you know this person. Her name is Helen Molino.
Oh yeah, she's in the Dr. Koleos's lab. She's in my co-supervisors is Dr. Koleos. Yeah.
Okay. Because I know her. I do know her, and I know her family. In fact, her uncle is our best friend, and so I remember talking to her about what was it last year or so, and she, I guess, is doing some work at McMaster or something like that, I think, right? And I said that, if you ever need access to a machine, obviously I've got, and then you guys at iBest also. Maybe she is already accessing, I don't know.
I think, I believe she said she did her master's at a different school, so it might have been McMaster. And she just, at the same time I began my master's, she came in as a PhD student. So I think she's now, maybe she's, I don't know if she's co-supervised by somebody from McMaster, but Dr. Koleos is also her supervisor. I've seen her in the lab this year.
What is the work that what does he do? What's the area of research that he's particularly in?
So he's like in the physics department at TMU. So Dr. Koleos' lab does a lot of ultrasound work. So I'm like an engineering student, so that's why my primary supervisor is Dr. Sai, an engineering lab. But because my bubbles have like applications with ultrasound contrast enhancements, that's where I kind of go to when I have questions about that kind of thing.
Dario, where did you study? Where did you do a lot of your work?
I got my undergrad from University of Belgrade in Serbia.
Okay.
And then I got my master degree same university, and then I finished PhD from the University of Edinburgh in Scotland.
Okay.
And then I worked here at the University of Toronto as a postdoc with Professor Aaron Wheeler and later on with Professor Milica Radicic before I got this job here as a manager of core facility.
Yeah, I recognize the name Wheeler Radicic. I can't remember. He's at U of T, is he?
Yeah, both are at
Yeah.
U of T. Yeah, Aaron is famous for the digital microfluidics.
Yeah.
Radicic, their lab works mostly in the field of tissue engineering,
Okay.
but also they use microfluidics a lot.
They're probably if I think Wheeler uses our platform through Craft. I think Radicic. I can't remember.
Yeah, they're both like users at Craft. Yeah.
Yeah. So.
And actually, I believe both are co-directors of the Craft.
Oh, okay. And then, what was your area of study while you were at Edinburgh before you came here?
Microfluidics still.
Yeah,
like
it was only.
But it was in the area of heat transfer. So I was studying like a small heat exchanger that was built on microfluidics channels in a silicon wafer with potential application for electronics cooling. So, and this project was about boiling in microchannels. So
Really?
that was the core focus, like that two-phase flow, including the boiling and the channel. So it's quite explosive.
No,
I went through many chips like before I finished.
And so this one, what was what kind of substrates were you using for your microfluidic devices?
Silicon wafer, like the
silicon wafer.
Yeah.
Okay.
So.
When was your introduction into 3D printing, Dario? Was it only when you worked at St. Michael's, or were you already doing it back in your studies?
During my postdoc, I started using 3D printers, like for printing, but those were standard filament FDM printers that we used for everyday some lab applications, like, you know. And then for microfluidics, I think, this is our first printer for microfluidics, but I got interested that very early when I started this position here to manage the microfabrication core, and I was aware of several companies. I mentioned there were not that many at that time. I'm not sure about now. There are more probably coming. Yeah. So we received like samples that was probably 7-8 years ago, including samples from HAMDIP that help us a lot to evaluate possibilities, and later on even to use some of those preliminary data to apply for the grant, so which was successful, and that's how we secured funding to get the printer in the institute.
Yeah, that is true. Niloofar, how about you?
The whole thing that besides microfluidic and fiber generation, that they are the main field of my PhD. Scott is working on bubbles, and the other one is ATPS, which is aqueous two-phase systems, which is exactly like water and oil, but in this case, both phases are going to be aqueous. So in biomedical engineering for biological materials, this is going to be a safe environment, not toxic. And also if you make your drug carriers or your scaffolds, at the end it won't need the washing steps to remove all the oil from it. So for the fiber generation, you need some thread distinct phases to make a fiber which is going to be uniform. So that's why we needed the two-phase system. And instead of oil, since Scott is working on ATPS, we were like, okay, why not to make fibers? And so for the fiber fabrication, one thing that is really, so I'm going into really technical part of it, but like, so my PhD, we wanted to make a microfluidic device, which we wanted to introduce a new technique to make different shapes of fibers easier with only one device, instead of like going to Cleanroom, changing the design, having like multiple designs to make different shapes of fibers. So if your goal is to make solid fibers, you can use the same device. And if you want to make hollow fibers, you can use the same device, just like the inlet solutions are going to be different. And also, like we showed that by changing pressure, you can change the dimensions, and the fibers at the end are pretty uniform. And also the other type that we made was droplet filled fibers. So there would be like some droplets inside a fiber. So those droplets can have something else inside of them. Like we can add some different drugs inside, and they can get released over time, or you can encapsulate cells. So this was the whole like idea for my PhD. And so for the microfluidic device, of course, we first went with the soft lithography. And so in general, soft lithography is really amazing. And also, like, one of the things that is good about it is how easy it is under the microscope to, like, it's pretty clear. You can see everything very clearly. But the issue was with soft lithography is kind of like the whole design is 2D. You can't have a 3D design, complex design in it. And so for me, which I needed coaxial channels to make fibers, it wasn't possible to just like use a create a mold, just spend one time at Cleanroom and then you're set for your life. It wasn't like that. So I had to afterwards, like after making the PDMS pieces, I had to insert glass capillaries, which was the really difficult part because I don't know. I think like we haven't found out any kind of technology that is going to be like cheap enough for in the lab to say that you want exactly this size of the glass capillary, and it's going to give you exactly that size with really fine edges. And so I had to like measure it with like my hands, and your nails are, they have to be really like short, and you have to like spend fining that glass capillary that you can't even see, and at the end you have to wash it carefully to be sure that all those glass particles are not inside your channels, and then you have to insert that glass capillary yourself. You can't use a tweezer because they are glass, and you shouldn't apply much pressure, so you have to like use your hands, and then with like tweezer you're gonna like put it inside and like move it a little bit around. And so at the end the nozzle won't be exactly the size that you want for all your devices, and the resistance in your channel depends on that. And afterward, you have to use a silicone paste to secure that opening that you created to insert those glass capillaries, which was really difficult, because if you're gonna add less silicone paste, it would be loose and there would be leakage. And if you're gonna apply a lot, it might clog the whole channel with the silicone paste. So after like spending some days making the devices, I had to throw away like 50% of like the devices that I made. So it was really frustrating. Yeah. And then by the first experiment, like, of course, microfluidic is really prone to clogging. And this is, I think we really need to, someone need to step up and spend their PhD on fixing the clogging of the glass capillaries. I was thinking of like those heart surgeons that they use those angiography things that they can insert something in the channel, so maybe open the channel, something like that.
Like a stent.
A stent, yeah. Like, because it's really creating some issues, and I think like it's the PDMS issue too. It's really prone to like everything to attach to it, especially for me that I was using alginate, and which at the moment that it gels, if it's going to touch the surface, it would attach, and you have to wash it carefully afterward to be reusable. So that was all the issue that I had, that I was trying to really change my, like, the next project to not use this device and like use something else, create some new ideas, which thankfully we ended up with a 3D printer that helped me a lot.
So when you look at 3D printing, obviously you're trying to replace the current system that you had only because it was painful, right? And it sounds like as if you really struggled getting glass capillaries in place. What was the base minimum feature sizes, or what did you need to have a 3D printer deliver for you in order for you to mimic what you were already getting using Cleanroom?
So the only important thing was having those nozzles that they're going to act as glass capillary that are going to, like, the next at the junction when the other liquid is, the solution is coming, there would be something that is going to prevent the solution to touch the walls. So that was the only important thing. And even so that the device, in the glass capillary, it's going to be like a round channel, but even so that it was a square, but because of the pressure and everything, at the end it would end up as a rod, kind of a fiber kind of thing. And the only thing that mattered to me was those nozzles to be exactly like the one that we had with glass capillaries. And because we are using pressure by increasing the pressure of, like, one of the inlets, you can squeeze your fibers. So it wasn't an issue to, like, if we can't have channels like smaller than 100, it won't be an issue for me, because if I want really thin fibers, I can increase the pressure. So the only thing that mattered for me was the nozzles.
And so as you were increasing the pressure, was laminar flow, or having very good laminar flow, very important, or could you overcome that issue?
Yeah, laminar flow is really important, and still, like, at the range that a 3D printer is going to give me, it still is fine, because for my device I need really big channels. Like with my even Photolithography, the height was around 600 micron and the width was like 450. And so here we tried around less than, I think, 200, 150 even channels. The first channel, I guess, if I'm not trying, but that was it for me. So that's why, like, it was really helpful for my project. But I could say that also another like really advantage of it that I found out later during the experiment was that it clogs less. Like the type of material it is, the alginate fibers, when they gel, they won't attach on the surface. It's like it was way easier to wash the whole device than the PDMS one. The only issue, of course, like not everything is perfect, that under the microscope, it wasn't always clear to see the phases. And for me, I really have to have a control over the phase and see that the thread is stable and what size it is. So like sometimes some of the devices, they were really kind of opaque and had residues in on the surface that was hard to see. But overall, I guess the whole thing had more advantage for me then just like that.
Did you end up doing any like surface modifications in order to help you see clearer in the device?
Not yet. It was the case of like making multiple devices, and sometimes one of them wasn't clear enough. But clear, it has like some edges that was it made me like I wasn't sure if the things that I'm seeing here is my like the distinct phases of like my solutions, or it's just like some edges, some like of that. But the interesting part was like I think like most of the time they were clear enough to see my faces and be able to work.
What was in terms of length? What kind of lengths are you trying to produce these threads in?
The device with fibers, sorry.
The fibers, sorry.
If you're talking about the diameter, it can be really like it depends on. I haven't tried more than 500 micron, but I think like that's even achievable if you are going to like that's the limit of the channel. If you are going to have like wider channels, then yeah, it's we can have that, or really thin fibers by like applying more pressure. But in case of lengths, that's something. The fiber generation is ongoing, so it's like one thread all connected, so you can cut it at the time that you want, but like the whole fiber when it runs, it's running and it's just one thread, so the length is really long.
Wow. And what are the potential applications for this technology that you've created?
So there my background is tissue engineering. For my my master, specifically the field was tissue engineering, and in tissue engineering the main component to make or engineer a new tissue, make a functional tissue, would be the template or the scaffold. So that scaffold need to mimic the environment that cells are going to have in the body, in their home. If you want to make a liver like a tissue, like you have to give them the same kind of like feeling or texture, structure. And most of the cells in our body, besides the blood cells, they are surrounded with extracellular matrix. And extracellular matrix is filled with like fibers, collagen fibers, elastin fibers. So they really like the environment, the scaffolds that they are in the shape of fibers. So that's why like there are lots of research that and techniques in tissue engineering that they try to make fibrous scaffolds. And so you could use those scaffolds based on the type of chemical that you're using. Here I'm using alginate, or you can make like dextran methacrylate fiber, gelatin methacrylate fibers, and based on like the application it would change. And or like you can change the dimension, the size, the shape of the fiber based on the final application. So for me, like the whole goal was to introduce a new technique, but in general, those fibers can be used as like for wound healing. You can, because alginate is one chemical that has been used a lot in wound healing. So you, in case of like hollow fibers, one interesting research that I encountered was they co-cultured those fibers, added endothelial cells in the core of the hollow fiber, and then co-cultured those fibers in an environment that had muscle cells. So at the end, those endothelial cells would sit on at the inside of the surface of the hollow fiber, and then the other one would be at the outside. And over time, those fibers would degrade. So they kind of showed that they can make new vessels and show that angiogenesis can be possible using this way. But the whole purpose is to make a fibrous scaffolds for the cells.
So then when you are fabricating the fibers, is biocompatibility in your device an important characteristic?
Yeah.
And then,
yes.
Okay, so then how did you had to do anything in order to make sure the device was biocompatible? And did you do like any biocompatibility tests, that sort of thing?
Actually, no. And I'm interested why no one in our review paper, like the paper for revision, they haven't mentioned that. No, we haven't.
Okay, we will not release this podcast at all until you defend it, so no one figures out these questions that they have to ask you.
But I think here that the way you make your fiber, basically, because you shield them with a two phase, so that core phase that eventually could come into contact, theoretically, actually doesn't get into contact with the material of the device itself, plus the resident time of the material inside the device is relatively small. So I don't think there is possibility of significant or any contamination. And second thing, we haven't tested like any, we are planning to do, but we haven't done any cell work with these fibers. That would be next step. We are just finishing a paper that hopefully will be published soon, but that's only about creating the fibers as a proof of a concept using these 3D printed devices.
Makes sense.
Yeah. So, and also with the previous one, the PDMS device that we made, I encapsulated cells inside the fiber. But as Dario said, even if it's going to be a little bit toxic, and if it's gonna depend on the residence time in the channel, it would be really slow and maybe like in way less than a second, milliseconds, it would be really fast. It would be like shielded with the next phase. Even though if you're going to like put them in the at first when they are coming through the channels, they might the cells might touch the surface, but it would be really fast. So, but yeah, that's something that we have to, of course, do in future.
We also plan to test different kind of resin that has biocompatibility or better biocompatibility than current resin, while making the same transparent device with the same level of features that is possible to achieve.
Yeah, so I think the CytoClear would be...
So that would be probably next step.
Yeah, CytoClear would be perfect for that.
Yeah.
Great. So I think we could easily say that, Niloofar, you did not fully defend your PhD quite well here.
This is why this is the practice round.
Exactly.
This is your practice round.
Yeah, exactly. I was thinking of that. So
it's good timing.
In terms of, you also mentioned a couple of times you were able to, is it correct? You were able to change the shape of the fiber itself? Meaning if you wanted a triangle or for some, the answer looked like no, you cannot.
No, triangle, I'm thinking how we can make that. I don't think that having a nozzle with different shapes is going to help, because I think that should be exactly at the moment of extruding and gelation. When they are coming out at the exactly at that time, they have to be in contact with the cross-linking, so they keep their shape. But here, what we are doing, we are using those nozzles to just keep them out of the wall, and after that, because of the pressure, they would form a round shape. But not with my device. With different shapes, the hollow fiber, core shell fibers, we made Janus fibers, and we made droplet field fibers, and besides core shell, it could be hollow core shell, all they have to be round.
They all have to be round. And then you're also encapsulating, you said cells. What other items, particles could you encapsulate inside there, and what would be the application?
anything like any drug, any kind of thing like that can be encapsulated inside. And one interesting thing about having, for example, the the Janus fibers that which one side is one material and the other side is another material, that we created that with the 3D printer with a Y-shaped channel. We made Janus fibers, so you can add one type of drug in one of them and another type in the other half. And the interesting part would be I recently read a paper that they, for the wound healing, because in wound healing we have different stage of the wound healing, that in the first stage you need to add these kind of drugs to promote those kind of cells to do, I don't remember exactly the exact stages, but yeah, the first stage you need to add these kind of drugs, and then it's gonna take 1 to 3 days, and after 1 to 3 days they are going to go completely in a different stage. So you need to release a different kind of drug. You have to be in a different environment. So they with core shell particles, instead of here we made core shell droplets, core shell fibers, but we are able to make core shell droplets, which is my next step. But so they made core shell droplets, which in the shell they loaded it with one type of drug, and then in the core it was another type of drug, and they control the drug release and the degradation of the shell and then the core in a way to be optimized with the stages of wound healing. So for the first 3 days, the shell would continue to degrade, and the content of the shell would release. And then after the 3 days, it would reach to the core, and then we are in a different kind of, we are having different materials and different kind of drug would be released at this point. So that could be one of the applications.
I think that's very important aspect, that versatility of fibers that can be made. So not just only one. First, we can tune the diameter of the fiber by, as Niloofar mentioned, by tuning, by using different flow rates and pressure settings on our supply materials. But also, it's possible to make hollow core fibers, droplet embedded in the fibers, and those Janus fibers, which for those who are not familiar, maybe they resemble those multicolored toothpaste. So we basically can make the fiber that is in a few colors, to say so, at the range of 100 microns or so, or a few hundred microns.
Yeah, the Janus name is coming from the origin is the Janus Greek god, which had 2 heads. And so in the nerds, scientists, for the droplets and nanoparticles, and also with the fibers, whenever they have a nanoparticle that exactly half of it is something else, the other half is something else, they would call it Janus, as from the Greek god.
Okay, so we've gone full circle. We've gone from Korean barbecue, Japanese barbecue, some other type of barbecue, to Janus.
To Janus goddess.
Yes, Greek mythology, Janus Joplin.
We just wanna prove that we're not just scientists. We have a life too.
We have personalities outside of our work.
We go outside sometimes, touch the grass, and go back to the lab.
Oh my gosh.
Yeah, I think using 3D printer now will let people spending more time outside instead of being in the clean room.
Yeah, yeah, they have more time now.
So they finally can have some social life.
I think you guys already touched on the next steps for you here and there. I guess, does 3D printing still fit in there? Is there kind of certain advancements you would want in 3D printing in order to kind of like help you bring you to that next stage
Yeah, I can
that you could think of?
I can kind of speak to this. So yeah, as I mentioned, like for my devices, like the flow focusing geometry is kind of the most difficult thing to fabricate, like to completely translate from soft lithography to 3D printing. So in the future with like resolution improvements and things like that, I really think that like it will really really help with accessibility to like the kind of research that I do with the microfluidic bubbles and generating these devices like in a much more efficient way and we can kind of completely eliminate the clean room reliance, which would be like the ultimate goal. Because for my work as well with microfluidic nanobubbles, so there's a lot of different ways that nanobubbles are generated. Another more common way is taking a vial and literally shaking it like crazy. It's called agitation, and it makes a bunch of bubbles, but they're polydispersed. Like they're very different size. They can range from like microbubbles all the way to like tiny, tiny nanobubbles. So, which is not ideal. So microfluidics offers this monodispersity, but it's not super widely studied. And I think that one of the biggest reasons is just because, the access to the clean room, the very like long, tedious procedure versus just shaking a vial and making bubbles. So I think if 3D printing can kind of completely replace like these photolithography, soft lithography dependence here, that will really be really important for advancing this field into like preclinical, clinical studies with the bubbles.
I think for me, too, if one issue that we had, we couldn't put the channels really close to the surface. They had to have like, I think, half a millimeter or so. I'm not sure exactly, but they couldn't be really close to the surface. So with the inverted microscope, and we want to like look at the solutions, the flow from on bottom of the device. The objective needs to get close to the channels, and that was making an issue. And also, if they could be more clear, to more transparent, and to see inside of the channel, that's one thing that would help specifically me with that I have like multiple phases in inside the channel. We like recently made a microfluidic device with 5 inlets. So inside I would be having 1, 2, 3, 4 phases, and I need to see the interface of each one of them, and it's kind of hard, and sometimes I have to guess, but overall, because I don't have to like cut the glass capillaries, I'm still okay with it. But if you can fix that, I would be happy.
Very important question. How many glass capillaries did you break?
So many.
I need a number now.
But I still like, I think like when you buy a glass capillary, it comes with so many of them, and you need a teeny tiny for each one. So even if you're gonna break like multiple of them, it's still gonna be okay. And you have to be careful for them not to go to your arms.
Yeah. You're also underestimating cost of stress.
Exactly. Like for that whole time, the thing that I was doing, because I was just like sitting next to the microscope, and for the whole day, I'm not like exaggerating, for the whole day I was grabbing a glass capillary that you couldn't see that I'm holding, and I was just like doing this. And one time, because like all my friends and family, they are from like in different countries, different cities, so I always video call them during these kind of like tasks and works that I have. So my friend was talking to me, and they were saying, like, what are you doing? We've been talking for 2 hours, and for the whole 2 hours you're just doing this. So that was my whole life for 2 years.
Oh my goodness.
I mean, Niloofar's project is an excellent example of using a 3D printer for the applications where it would be very difficult to use standard like soft lithography or photolithography processes. And that's something that we are looking into future to identify those projects that are difficult or impossible to do other ways than 3D printing. And I think that's great opportunity here.
I remember seeing I think the first draft of that STL when it was sent over for us to take a look at, and I was very curious as to exactly what on earth this thing is supposed to do and how it all fit. And I'm so glad to have had this opportunity to even, how it comes full circle. It really is amazing how the world works, doesn't it? No. I think we have come to the end of this conversation, and it's not really an end of the conversation, but I think this phase of the conversation ends now. But I think I'm so glad that I had a chance to talk to all three of you. You highlighted the type of research that is being done and that a lot of people don't know about. I know me as part of the, on the outside, definitely doesn't realize that this is the type of complex research that's being done. And it's amazing that you guys that we had a chance to listen to it, about it, and all the struggles you had and the successes you had from your hard work as well. Thank you very much for coming.
Thank you so much for having us.
Yeah, thank you for having us.
Thank you for having us.
And that will end today's episode of Big Ideas at Microscale. My name is Hemti Patel, and my co-host, Robin, will say goodbye for now.